I'm Alex Gramfort. I'll be also giving this tutorial with Hubert Banville this afternoon. Actually, this afternoon for us, probably this morning for many of you. And so we have a little less than 3 hours now to cover MEG and EEG data processing with a strong focus on, let's say, machine learning applications. All right. So if there's anything, any question you may have, we have Hubert who will follow either the chat here or the Discord channel. So feel free to ask your questions here. And Hubert, if there's any questions that are popping up along the way, just please do not hesitate to interrupt me, and so we can have a small chat in between, which probably will be also nicer for me rather than talking for 2 or 2.5 hours without feedback. All good? All right. Okay, so you should have all the materials in this page. Okay, so there's a slide deck that I will cover here, and then there's a number of notebooks. It's absolutely unrealistic to go over all the notebooks in 3 hours. But let's see where we're going. And I guess the more feedback I have from you, the more I can select where to look in these notebooks. Probably the most ambitious one is the last one, which is a tutorial doing deep learning for sleep staging using PyTorch and MNE-python. All right. So I'm going to put my go full screen. I won't see anything. I will not have any visual feedback. Hubert, if there's any issue, you can text me if there's any problem. All right. So let's step back a bit and see, okay, where we are with this tutorial. I want to cover a fraction of electrophysiology, which is, as illustrated here, electroencephalography, EEG, and MEG. And I'll also briefly mention SEG. Just give me 1 sec because I cannot see my cursor, and this is problematic. Slideshow. All right. Yes. Okay. So now you should see my cursor here. So okay. So we'll be covering EEG and MEG, which I will explain in a minute what they are. Okay, so here's first is 2 short video clips. What you see on your left is a temporal movie of EEG as interpolated over the skin surface. What you're seeing here is some electric potentials in volts. And what you see on the right is MEG. So MEG is recording on a helmet that is not attached to the skin, but just a few centimeters away. And what you're measuring is the magnetic field, which is measured in Tesla. Okay. So the game is to understand how these data are produced, what analysis do you do with this data, and typically what types of machine learning tasks can you do on this data. So the key property of electrophysiology is related to time, the time dimension. As opposed to fMRI, which is mostly a spatially well-resolved modality, when you speak about electrophysiology, what people remember is the temporal resolution. So what you see here is a number of empirical data. What you see here is EEG during sleep, where you see so-called micro events, microstructures like sleep spindles or a K complex. What you see here is the so-called mu rhythm that is produced in the motor cortex and has this mu shape with this very sharp trough, and that's what gives the name mu. And what you see here at the bottom is some invasive recording on a rodent, where you see some coupling with some high-frequency bursts that always appear, or at least are stronger, when you're on the top of a slow wave. Okay, so you have this interaction between low frequencies and high frequency, and this is what people call cross-frequency coupling. The take-home message of this slide is that most of the information is actually present in the time dimension, and the morphology is probably more complex than what you think. Another example that is relevant to clinical practice is EEG during general anesthesia. So what you see here is an example of so-called burst suppression. So if during general anesthesia the drug dosage is too strong, then people can produce these types of patterns recorded with frontal E electrodes. And you see that you have some bursts that are followed by kind of a flat signal. And this is typically something that can be problematic. And depending on the types of drug that you give to people during general anesthesia, you introduce some different properties. And what you see here is the time frequency representation, where here this is a typical signature of people during propofol, or here during ingesting sevoflurane, which is a gas, and other drugs that you see here. Again, what is relevant here is the so-called spectral content, or the space, and also the time and frequency, and this is the spectral signature that you can recover with electrophysiology. All right, so I wanted to focus a bit on machine learning, so I will just do a bit of advertising for this work that was also done in collaboration with Hubert, who is here this afternoon or today. Where in this work was collected a lot of papers applying deep learning on EEG, and this for me is interesting to show what types of applications and the diversity of application that people can have with EEG. So you see some application related to brain-computer interfaces, but also some clinically relevant applications like epilepsy or sleep. And also, let's say at the low level, that can have a broad impact, which is to improve the processing and typically pre-processing, automate some types of processing in EEG data analysis. An example of a fairly old, but very, for me, significant example of decoding or classification of states using EEG. This is an example of so-called motor imagery. So you ask people to think about moving their left hand or their right hand without actually moving it. And here we're looking at so-called event-related desynchronization. So this is how the power in the signal, typically here between 9 and 13 hertz. Okay, this is the evolution of the power in the signal as a function of time. And you see that here, looking at a single time course, you have a stronger decay or a stronger desynchronization when you have your right condition versus the left condition. Okay, and here you can see this in terms of topography, and you see the spatial map, which we call the topography, varies between the two conditions, between left and right hand imagination. Okay. All right. Another example of machine learning on EEG is a so-called P3 speller, where you have some letters that are flashed on the screen, and by having the subject focusing its attention on one letter and recording the so-called P3 wave, then we can find out what letter the subject was actually attending to in order to spell. Here you see letters. So first you have H-E-L, and I guess that could be the word hello. All right. So in order to understand how to process data, you need to understand how the data is actually produced. So I'll spend a bit of time on explaining the background of EEG and MEG, and hopefully this will clarify the data that you will manipulate later on. All right. So I guess in this in the audience of Maynard, this slide is pretty obvious, but let me state the obvious to insist on one aspect. So here, this is just an axillary slice from brain. You have the white matter, the gray matter, and the cell body of the neurons is located here in the gray matter. And this is where the signal that we pick up with EEG is coming from. At least this is the common knowledge so far. All right. So in order to understand how the signal is produced, you need to understand a small dimension of physics. So here I'm just going to illustrate this for the case of the magnetic field. If you have some electric charges, so let's say you have some electrons that are moving along a wire. So imagine that you have some current in this wire. By just having this current flowing through this wire, it induces in the vicinity of the wire some magnetic field, okay? And this magnetic field is here is a rotating field that rotates around the wire. To understand how the field rotates, you need to look at this picture. You use your right hand, also called the right hand rule. And so if the intensity of the current is in this direction, then your thumb is pointing in the same direction. And using your right hand, you follow the hand, and that gives you how to follow the field lines of the magnetic field. Okay. So the take-home message is that by having some currents that are flowing along some linear structure, we have some induction of a magnetic field, and it will be the same for the electric potential. All right, so where are these tiny wires located in the brain? They're actually located in the gray matter. This is a small zoom on some neurons located in the gray matter. These neurons are so-called the pyramidal neurons, the pyramidal cells, that tend to have a fairly linear dendrites, okay, which is structure that you see here behind the red arrows. And all these tiny dendrites, when you have some ions that are flowing through them, okay, will produce some tiny currents. And by summing all these tiny currents, you're going to produce an electromagnetic field, which is strong enough such that you will be able to pick it up using EEG electrodes and MEG sensors. What you're measuring is actually something that has a unit. So here, what matters is the intensity over the distance. So the quantity of interest is so-called the moment of the so-called electric current dipole. That is a model to model these types of assemblies of neurons. And the intensity of this electric current dipole, or the strength, sorry, of this electric current dipole, is expressed in amplitude of the intensity of the current times the distance. Okay, so here you would say that in the typical brain signal, that would be on the order of a few nanoampere meters. So here I would say 10 or 100, and we'll see this in real data later. All right, so these electric and magnetic fields, they are recording using EEG device and MEG device. So EEG device, you put some electrodes on the skin, and what you're going to measure is the difference of potentials between two electrodes. So you need a reference. You need the zero reference, which can be on the mastoids, okay, so behind the ears where you have a thick bone, or they can be wherever you feel. It gives you a clear picture of the signal. And in the context of MEG, what you're measuring is the magnetic field. So here what you're sensing, what you're observing is a scalar field, which means that every location you just have a float, which is your strength of the potential, where here in 3D, the magnetic field is a vector field, which means that every location, the field has a strength in three directions, X, Y, and Z. And so when you measure it, you put a sensor in a given position and a given orientation, okay, which means that at one location, you can sense the field in three directions, X, Y, and Z, for example. All right. A small remark, still the common MEG system is based on so-called squid sensors, and these sensors that are in very low temperature, so in the supraconductive medium, which is a liquid helium at a few Kelvin, and this is an example of device of an MEG device. All right, so the sensors that you have to measure the MEG is either magnetometers that will measure directly the magnetic field in one position and one orientation. You will get signals in Tesla, or so-called gradiometers that can be either planar or axial. So here, a planar gradiometer will measure the difference of magnetic fields along a specific direction, which is here the y direction. Okay, so you measure the field here minus here. You compute the finite difference between the two. That gives you the derivatives of the field perpendicular to the square here. And by measuring this field here minus here, you measure the derivative of the BZ vector field with respect to the y direction. And then you can do the same thing for x. So on the data that we'll play with later, you have 3 time course that you obtain, 1 magnetometers and 2 planar gradiometers. But for example, if you use a CTF system that typically is available in McGill in Montreal, you have here axial gradiometers, and what you're measuring is the field between here's a coil that will be close to the brain minus a coil that is a few centimeters away from the brain. What is important to understand is that these signals, when you collect EEG and MEG, what you see in the signals is actually mostly noise, and the true signal from the brain is actually dominated by the noise, at least on the raw signals, or at least very close to it. So the issue is that these modalities, they are sensitive to so-called physiological noise and peripheric noise. So typically the environmental noise is the urban noise coming from landlines, cars, any electronic devices that you have next to the sensors, but also physiological noise, like the fact that you have the heartbeats, you have muscles that are active, and these dominate in amplitude what you care about, which is typically epileptic spikes or brain evoked responses. Still, what is good is that the sensor noise is lower than what you want to measure. Okay, so it means that in order to get good data, you need to shield your environment, you need to shield your subject from the environmental perturbations. So how do we do this? We use a so-called shielded room, which is here illustrated here. So it's here you have very thick walls, and that allows you to either passively or actively kill whatever perturbation from the outside. So if you look back and you say, okay, how was it possible to record, for example, the first MEG data in the 60s? So this is a picture of David Cohen on his shielded room that he built in his lab at MIT in the 60s. And so David Cohen and James Zimmerman ushered in a new era of biomagnetism when they measured the magnetic field from a human heart using a superconductive quantum interference device, or a SQUID. It's the first use of a SQUID with a human subject. The experiment threw open the doors to medical applications of the technology, the possibilities of which researchers are still exploring today. So an important, for me, lesson from this is that the SQUIDs were there, and what was missing to get good data was the shielded room that David Cohen was an expert in. And this allowed, now a couple of years later, in 1971, to record the first brain signals, not the heart, but this time the brain, using MEG. So this is so-called alpha waves. And here you have the eyes of the subject that are open. Then the subject here starts to close his eyes. And what appears by closing the eyes is you see these bursts that are also very clearly illustrated here. Okay, so it was by having an intervention like eyes open or eyes closed, it was the proof that MEG could record the brain with here, as you see, with a very good SNR actually. Okay, so now if you look at an MEG system in those days, this is the system that is available in Paris in the Neurospin Imaging Center. This is a so-called Electra vector view system. So the subject will sit here in this chair, either like up or down, and you will measure up to 306 MEG time courses, planar gradiometers and magnetometers. And you can also simultaneously record the EEG by just inserting the EEG cap in between the head and the dewar that contains the MEG sensors. So once you have collected your data, this is typically what you see. You have the time courses of here in the context of EEG. So each EEG has a specific name. And here what is written is FP1 minus ref. Again, what you measure in EEG is a difference of potential. So here, this is whatever is measured on the FP1 electrodes minus a reference electrode that was specified either during the acquisition or during processing. Let's say in EEG, the order of magnitude, let's say if you do sleep, you can have really a handful of EEG electrodes, let's say 1, 2, or 4, but really usually not much. In the cognitive EEG study, I would say between 60 electrodes, or if you have this access to these so-called high-density EEGs, you can have hundreds of EEG sensors. In the context of MEG, you have much less flexibility. You have only a few types of devices. I mentioned the vector view from Electa will give you 306 sensors, or if you have an older system, that could be roughly half of this. And the sampling rate is on the order of, let's say, 250 hertz for EEG, up to 1 kilohertz for MEG. You can have MEG recordings with more than this if you're interested in so-called high-frequency oscillations. But I would say it's more the common practice is to have 1 kilohertz for MEG. So you have a high temporal resolution, but the question is, what is the spatial resolution of this? So here, this is the field map, so-called topography of an EEG activations recorded on a subject that is stimulated with so-called median nerve stimulation. So you stimulate electrically the wrist of the medial nerve on the wrist of your subject, and it's typically what you see. You have this positive deflection and negative deflection. And here, if you understand the physics of EEG, it means that you have your sensor, your source, or your equivalent current dipole, your source, that is positioned below this and pointing from the back towards the front, a bit tilted upwards. This is in 3D. This is now in 2D. And here, same story. By looking at these two patterns, these two blobs, the source is actually in between. What I want to stress here is that you should never interpret the location of your source just by looking at the strength of the EEG. If you see a big red blob here and you say, okay, that's a frontal activation, you will be very wrong. It turns out this is really a motor activations. Again, look at the so-called dipolar patterns that you see here. All right. Another remark is you see that it's fairly smooth, so the spatial resolution is let's say, a challenge. So I can do the same types of plots, but now taking MEG. So now this is not the same subject, but a comparable protocol, still medial nerve stimulation, looking at the peak of the evoked potential. Again, you see this so-called dipolar pattern with red and blue. And here, if you use your right hand, so you use your right hand rule, so it means that your dipole is actually sitting in between and here pointing upwards from here towards the nose. And this is the comparable location between this and this. You see that going from EEG from EEG to MEG, you have a 90 degrees rotation of the pattern. But also with MEG, the pattern is kind of smaller and narrower, which suggests that MEG has a better spatial resolution than EEG. What I mean by this is that if I have two sources which are here, let's say, away from 4 or 5 centimeters, they are less likely to spatially overlap with MEG, whereas with EEG, they can be completely superposed, which will make it really challenging to disentangle them. Okay, MEG in the end looks like this. It's just a 2D array where the rows of your array are the time courses, and the columns of your array are all the measurements on all the electrodes at a given millisecond. So to produce a topography, you slice your data and you extract a column from your, let's say, NumPy array of time courses. And now if you want to look at the time course, you extract a row from your 2D NumPy array. And here you see a waveform. At T0, you have a stimulation. And this is your recording. Here on the planar gradiometer, you see there's something that is recorded in Tesla divided by distance. So this is femtotesla per centimeter. This is a planar gradiometer. And you see that the SNR is really excellent. So this is obtained by so-called averaging. I will comment on this in a bit later. But that gives you an idea of the signal you will obtain. A very sharp transient effect at the beginning, the early evoked component, and that's slower and then slower waves coming later before having a signal that goes back to baseline, so close to zero, which is where it started from before the onset of the stimulus. Okay, so the data acquisition example, you have different types of protocols. I mean, of course, you can do spontaneous data and resting state data, or just monitor patients suffering from epilepsy, or just like monitoring people when they sleep. But I'd say a lot of the experiments are actually conducted with a clear protocol, where the subject is experiencing a number of stimuli and has to sometimes perform some active tasks. What you see here in the stimuli is that they can be auditory, visual, somatosensory, that can be displayed on the screen or with audio. Then the subject has to do a specific task, attend to certain stimulus, to react, for example, by pressing a button. And the behavioral response, so basically whatever the subject is doing, can be recorded. So by finger movements, by pressing buttons, or sometimes using speech, although talking in the system can also create some challenging artifacts. At the end, if you work in this paradigm of so-called stimuli or task, MEG and EEG, what you have is chunks of data. So this is what we will call epochs in MNE-python. So every epoch is going to be a slice of multivariate time series, so a slice of MEG or EEG signal. Here, this represents the onset of the stimulus, and you will measure on all of your MEG or EEG sensors the response or the signal that is following the onset of the stimulation. What is illustrated here is an epoch which has an artifact. You see that the one sensor has a big deflection, and this suggests that this epoch can be maybe thrown away because it contains an artifact. An important information is that I would say almost all the artifacts that you find in EEG and MEG, they are amplitude artifacts. Okay, so what matters in order to remove these artifacts is to find to identify where you have huge amplitude artifacts or huge variance that you collect, and this is a source. This is basically the signature of artifacts. Okay, so let's talk a bit about preprocessing. So these are your continuous data. So these are MEG. You have two colors. You have the light blue that you see here and the dark blue. So the light blue, they're actually the planar gradiometers. You see they have a number that ends with 2 or 3. And here you have the MEG 0121, which is this signal that you see in dark blue. And this is actually a magnetometer. So here, what you see in dark blue is something in Tesla. And what you see in light blue is actually something in Tesla per meter, because it's a gradient of the magnetic field. And in parallel of this, you record here a channel which is the EOG 61, which will be the derivation that you put on the eye to know where the subject is actually blinking, because this is a source of artifact. And you can also record here at the bottom the EKG, so electrocardiogram, which also contains a source of artifact. So usually in a class, I would ask you to tell me what you see. Here, I don't really see you, so I will assume that you are trying to do what I'm about to ask you, which is, okay, just looking at this signal, what do you effectively see, and what types of problem do you foresee by eyeballing this data? I will pause now and take any question that you may ask. Feel free to type your question. Hubert, just unmute yourself if you want to read any questions there may be in the chat. Is there any question?
Currently, no question in the chat.
Okay. Give you 10 more seconds to ask any questions you have. And maybe just to still try to make this a bit interactive despite the distance, can you put in the chat just a few keywords of artifacts that you see in the data? Hubert, any activity?
No activity for now. Also looking at Discord. Okay, yeah, so we have some people saying blinks, eye blinks.
Yes. So the blinks are typically here. Okay, so this is one source of so-called physiological artifacts. There's other artifacts that you see. Typically, that you will see them in the dark blue channel, so in the magnetometers. Any more activity on Discord?
So we have someone saying high frequency noise and baseline drift.
Exactly. So we have so we have high frequency noise. You see that the signals have these wiggles that suggest that you have some buzz on the signal. You have these slow drifts that you mostly see them on the magnetometers, like these very slow fluctuations. But also, if you zoom a bit, here you see these types of peaks in the signals, and you see they are perfectly aligned with the EKG, and these are just corruption from the heartbeat into specifically the magnetometers. So this is what I illustrate here. These are the blinks. This is the buzz, the line noise, which in North America, that's going to be 60 hertz. If the data is collected in Europe, it's going to be 50 hertz. And then you have the drifts. So after doing typically a bandpass filtering by just doing a high-pass filter with a cutoff at 1 and a low-pass filter at a cutoff of 40, which obviously get rid of the line noise, and here the high-pass will kill the slow drifts, you recover, let's say, cleaner signal. You did not get rid of the blinks, and you did not get rid of the heartbeat. But this looks like a signal that you could start to effectively at least visualize and potentially analyze. Okay, so there are many ways of doing artifact correction. I will just mention the two most popular ways. The first one is called signal subspace projection, where the idea is to identify the subspace that contain the artifact. You do this by basically computing a PCA, a principal component analysis, on the block of data that contains mostly the artifacts. So, for example, if you want to remove the heartbeat, you're going to get a bunch of signals that are time-locked to the heartbeat, and then apply a PCA on this data in order to estimate a subspace. So here your data typically lives in dimension 306 if you have a vector view system. So your heartbeat maybe will span a subspace of size 1 or 2, which means that you will project out your signal out of this subspace. So you will go from a data living in the subspace of dimension 306 to a subspace of dimension 304. Okay, if you remove 2 directions because you project out from the subspace that contains the heartbeat. So this is something that is particularly employed in MEG, I would say much less in EEG, where the notion of independent component analysis is fairly advocated, and that allows you to remove artifact without doing orthogonal projections. Okay, so the argument is that if you have your signal of interest, which is not completely orthogonal to your artifact, by doing SSP, you're going to kill your signal of interest, or at least attenuate it too much, in which case ICA could remove your artifacts without attenuating as much your signal of interest. Okay, this is now a bit unwavy and kind of an argument of authority, but I would say there's a number of evidence that this argument is actually valid on many empirical data. Okay, so once you've cleaned up your data, what you obtain is the so-called clean data, where now you have no more drifts. You have the artifacts of the blinks which have been removed, and then the heartbeat also, which is almost invisible at this point. All right. So I'll say a few things about power spectrum estimation, which is a bit at the core of basically identifying the signal of interest with MEG and EEG. So I will give you 30 seconds to think about this question. I assume that some of you have heard and have had some exposure or training on signal processing. And let's say you want to compute the so-called power spectrum density, okay, which is a function that is the strength, okay, so the L2 strength of your signal as a function of frequency. So you want to obtain a curve that will quantify how strong in your signal for different frequencies. So this is the so-called power spectral density. And now I give you 5 minutes of data, okay, at your data in sample at 1 kilohertz. And I ask you to compute the power spectrum density of this. So I guess one natural answer, at least from some of you, would be, I'm going to compute the Fourier transform of the signal that can give you the Fourier coefficients, and I'm going to take these Fourier coefficients, square their magnitude, and that's going to give me my power spectrum density. The truth is that nobody does this in practice. The reason is that the estimating the power using just the Fourier on the entire signal will give you a very noisy estimate of the power. So the way power spectrum density is typically obtained on long recordings is using something that is called the Welsh Periodogram. Okay, so periodogram is the name for the estimate of your energy as a function of the frequency. And the way you will do it is by windowing your data, let's say by taking a window of, let's say, 8 seconds, 10 seconds, potentially with some overlap, and obtaining and computing the Fourier transform of your 10-second windows, compute the squared magnitude of your Fourier coefficient. So you obtain one such squared coefficients for this window, then this one, and when you will average all of these power estimates, and that will give you the so-called Welsh Periodogram, which is a good estimator of the power spectrum density on long recordings. And when you apply this on real EEG and MEG data, what happens is that you usually see something like this. So you see a so-called 1/f power spectrum. So if you look at the power spectrum density and you display it in decibel, okay, so it means that you take the log of the squared magnitude of your Fourier coefficient average over multiple windows, and you display it as a function of the log of the frequency. So this function is actually in log-log. It's a log-log plot. You see something that looks like a straight line. Okay, so of course you have a number of peaks that emerge. These peaks can be typically artifacts. So here you have a peak at 60, a peak at 120, a peak at 180, and these are just the line noise and its harmonic. So the line noise of 60 Hertz, the first harmonic, the second harmonic, etc. But anyway, you find this 1 over f slope. And one thing I would like to stress is that maybe your signal of interest is, let's say, at 20 Hertz. It's very possible that the 20 horsepower is much smaller than the power on the low frequency. Okay, so this 1 over f slope will make it so that if you just look at your signal, when you look at your data, what you will see is just the amplitude of the raw signal. This power spectrum estimates where the strength can be the strength of the curve can be dominated by very low frequencies. What you will see when you eyeball your raw data is mostly the low frequencies, because this is where the power is the strongest. Okay? So I don't know if it's clear. I cannot see you right now, but I want to insist on this power spectrum density will tell you how much the raw signal is actually dominated by certain frequency. And imagine that this peak will go very high. Okay, imagine that this peak arrives here. If this happens, it means that if you look at your raw data, you're going to see mostly the harmonic at 120 Hertz. Okay, so if you've ever done some EEG and EEG analysis, or if you had any class or read any paper, usually you've heard about gamma, beta, alpha, theta, and delta bands. Okay, so sometimes you have low alpha, low beta, high beta, low gamma, high gamma. But let's say the big picture is gamma will give you corresponds to the high frequencies, are believed to be, or at least it's the evidence that they are probably the spectral content that is the most related to actual spikes. And then you have the alpha, so beta. Let's not say too much about beta for now, but alpha is something that typically we saw on the picture from David Cohen, where you had the eyes open and eyes closed. And here, delta would be lower, like 104 Hertz. And typically in the anesthesia data, you will have some strong delta components. All right, I will. This is kind of a first introduction. I don't know if there's any comment or any question at this point. And then I will do a bit of machine learning on EEG and MEG.
So Alex, we had two questions on artifacts.
Yes.
One was about the slow drifts and what they mean.
So typically your squids, they are sensitive to environmental perturbations. Okay, so if you have anything that is slowly moving, or any electrically charged structure that is moving in the vicinity, it will produce these very slow global field changes that you will see in all of your magnetometers at the same time. So they are really I would say the drift that you see in the raw MEG signals, and you typically want to kill them during the acquisition. This is why MEG, you always have a high pass even during acquisition, because if you don't do this, then the signal will drift progressively and hit the signal will be clipped at the dynamic range of the signal. So this is why you always need to do this high pass filter, because these drifts appear mostly in the magnetometers. Now they are much less present in the gradiometers, because when you do a gradiometers, you do a difference between two neighboring sensors, and by doing this difference between neighboring sensors, you will cancel out the artifact. And I will come back to this in a minute. And you had another question.
We also had a question from Willie. How do we know if the artifact correction did not erase the true signal beneath?
That's a very good question. And I guess every time you remove artifact, you will remove a fraction of the signal. The question is, what should you do? My answer is that on any processing pipeline, and people may object to this, is do your entire processing pipeline with very little pre-processing and very little data cleaning. and go to the end of, let's say, an effect that should be there in your data. Let's say if you do auditory studies, just do a control, a full experiment, like a full processing pipeline until you see evoked components of auditory activations. And this is the thing that it must be in your data set. And then you can start to add a bit of pre-processing and say, okay, by doing this very standard or like typical pre-processing, do I still see what I should be seeing? Like, for example, the auditory evoke response. Is it cleaner or is it nicer? And I usually say, okay, look at the effect that is kind of must be there, rather than looking at the effect that you want to show for your particular study, which is a bit dangerous in terms of double dipping and tweaking the data until you find exactly the effect that you want. I don't know if it makes sense or if the answer is convincing enough.
We actually have a follow-up question by Willie.
Yep.
So is there a method commonly used to estimate the accuracy of correction after artifact removal and potential bias due to the process?
Let's say if you do learning, or if you do a machine learning task, it's your figure of merit is clear. It's your classification accuracy or your cross-validation score. But now on a number of, I would say, cognitive studies where this is not really the approach that is employed, I would say it's less clear. I mean, you need to have one figure of merit. At least this is what makes your life easy. One figure of merit that you can look to say, okay, is it better or is it worse? I mean, is your effect of interest now clearer? Again, making sure that the effect that you are, or the quantity that you are looking at is more control than the specific question that you want to address to avoid the multiple comparison issue and the risk of overfitting your particular contrast or score that you want to report in your paper.
Thanks. And we have one comment by Pierre Belec here, who is shocked as an fMRI person that you're not looking at 0.08 hertz.
Maybe there's something to find out. I mean, Pierre, you have some data during the tutorial, so I encourage you to see if there's anything there. Although the data may have been high-passed, so you will see just floating point errors. But any other comments?
I think we're clear for questions right now.
Okay. I hope, Pierre, that you're convinced that MEG is a lot, and MEG and EEG is a lot more fun than fMRI, and that you should invest more time on this. But I cannot see your face. I hope you're smiling. All right, machine learning on EEG and MEG. So I want just to do a bit of commercial and advertise some paper that was written by a number of the MNE folks who worked on the decoding submodule of MNE-python, where in this work we are kind of discussing, and with a number of references, the so-called encoding and decoding paradigms on so-called neural dynamics, so basically electrophysiology, EEG and MEG. And also this review paper, which I already mentioned, where Hubert did a huge amount of work in the early days of his PhD with me, like looking at all these attempts and papers and studies using machine learning, and particularly deep learning on EEG. All right, machine learning on EEG and MEG, the big picture. I would say, let me simplify things. We can we can separate machine learning into big subdomains. Okay, I'm gonna on purpose simplify things, but let's say we have two possibilities. Well, the first possibility is so-called unsupervised learning, and in the context of EEG and MEG, it means it can be used for denoising, or it can be used for data exploration. And the types of methods that are behind this unsupervised learning on EEG and MEG is PCA, which I already mentioned in the context of so-called signal subspace projectors, or SSP. But you have also ICA, which I also mentioned, convolutional sparse coding, which I will illustrate in the next few slides, but also many others. And I can mention, for example, SSD, which is spatial spectral decomposition, but there are many more. And then you have the supervised learning paradigm that you can apply to EEG and MEG. It can be useful in cognitive neuroscience to know if there's an effect in your data and when this effect is present or in which frequency band. It can be used in the context of brain-machine interfaces, but also in the context of, I would say, personalized medicines, where EEG and MEG can be used as a biomarker of certain clinical condition. And the method that you have in this category, very historically employed, is linear discriminant analysis, LDA, which is a linear classifier, which is a generative model with Gaussian, like a multivariate Gaussian models for the classes. Logistic regression, which I will illustrate a bit later. And also, historically, the first decoding studies on brain signals were done with linear support vector machines. I would say these days, most people just use a plain logistic regression. But there are others, and I would say often less known, especially in the cognitive neuroscience world, which makes me sad. And I'm hoping with this tutorial to convince you that it should be employed more. So CS common spatial patterns are a way to decode so-called power-induced effects. We mentioned, for example, motor imagery would be a typical case for this. But also people have applied, because you have signals, so convolutional neural networks are very commonly used. But also, we'll mention a bit later the idea of using so-called Riemannian metrics or Riemannian methods, working with so-called covariance matrices on EEG and MEG. But also, if you extract some handcrafted features on your data, you can also use any robust classifier like a random forest in order to predict some types of clinical outcome given your EEG and MEG. All right, so I will start by showing a few papers with some examples that you can just click on the link at the bottom of the slide and just look at the tutorial and download the notebook and just run it on your machine or on Colab to replicate the figures. I will explain a bit more what evoked and induced activity are and how decoding can be applied to identify effects that are either evoked or induced. Then I will do a bit of math and a few equations to give you the background on linear models, but also how evoked activity can be studied, but also induced activity using either CSP or Riemannian methods. And I will conclude afterwards. And then we'll do the hands-on. All right, so let's start with examples of applying machine learning on EEG and MEG. So this is now starts to be a fairly old paper published in Journal of Neuroscience. And it's a visual stimulation. So you have different stimuli that are presented to the subjects. So they're actually gradings that can be oriented like this or like this. So you have two orientations. And then for each orientation, you have different spatial frequencies. So you have two factors, either orientation or frequency. So what the author of this paper did is they took the MEG and looked at every millisecond how each of the pair of conditions could be separated, okay? So see this, for if you've studied fMRI, see this as a searchlight, but now in time. So you take the data for all your trials, all your epochs, all your stimulus presentation at a given millisecond, and you have basically your data, which are in dimension, let's say 306, because you have 306 MEG channels. So you have n features, which is 306. N samples is the number of epochs. And a feature is just the amplitude in, let's say, Tesla per meter or Tesla of a given sensor at a specific millisecond, okay? Then you run a logistic regression to classify a pair of conditions, and you report the cross-validation score as output. So this is what you see here. You see that during baseline, the decoder is at chance level, okay, so 50% accuracy. And then after a few milliseconds, it ramps up, and you see here that roughly at around 40 milliseconds, it starts to ramp up. So this allows the authors to say that the time result classifier using a 20 milliseconds moving window exceeded chance level at 51 milliseconds, the later edge of the window for spatial frequency, and 65 milliseconds for orientation, and 92 milliseconds for rotation direction. Okay, so it means that the earliest effect that can be decoded was actually spatial frequency, so classifying low spatial frequency or high spatial frequency, then orientation, and then the rotation. Okay, and this is also illustrated with this confusion matrix, where you see how much you make mistakes by here. This is the same stimuli here. So if your matrix is diagonal, you're good. And what this matrix shows is that you make mistake by confusing this stimulus with this one, which means that you make a confusion with the orientation, but you don't really make a confusion when it comes to spatial frequency. So your effect size is much bigger for spatial frequency than for orientation. Okay, so to go a bit beyond this, this is a paper that we did with Jean-Rémy King and co-authors on using these types of temporal-based decoding and introducing the generalization across time, where here you learn a classifier at the given millisecond, and rather than just testing it at the same instant like we did just before on the previous slide, now you see how your classifier generalizes to a different time instant, still on different trials, on different epochs, but it's really shifting the features of the test data by taking the features that are further or backward in time, or at least at the different time instant. And you have a number of, you produce this kind of 2D generalization across time. And I invite you to read Jean-Rémy's paper to understand how to interpret these types of pictures. But again, if you go to the bottom, you have a link that you can click, and that allows you to look how to do such analysis using MNE. So just to illustrate how this analysis reveals difference between two effects. So here, these are so-called local deviance in the local global paradigms. And you see that the effect is fairly limited in time, whereas the global deviation, the global changes into the sequence of audio stimuli produces a decodability which is much more broad in time, and also generalizes in much more diverse time instance. All right, another study is a work led by Radek Kishi when he was at MIT, and he looked at another way to quantify discriminability using so-called RSA. And the idea is to have, here he has, I think, close to 80 or 90 types of stimuli, which are categorized as being either animate or not. If it's animate, it can be human or non-human. If it's human, it can be body or face, non-human body or face. So you have a hierarchy of attributes that are attached to every stimulus. Then you train your decoder at every millisecond to discriminate between pairs of stimulus. That allows you to produce a matrix like this, which is your cross-validation score of every pairwise comparison. You have a matrix like this at every time instant. And here you can look at how much your matrix, your empirical matrix of covariance of cross-validation score correlates with this prototypical matrix, which will be like a contrast in RSA sense between animate and inanimate. And you see that you have a stronger effect for this contrast between animate and inanimate at 157 milliseconds before it fades down and goes back to baseline. You can use a different way of contrasting. Now it's contrasting natural versus artificial inanimates. And you see that the effect is weaker. So here you have the peak was bigger. Now it's a bit smaller. But you still have a significant effect that is time resolved at 122 milliseconds that before it fades down to 0. Another example of how to do machine learning on EEG and MEG is using, here it's actually an encoding model where we are training a model from the speech spectrogram. Okay, so this is the spectrogram of your speech, and you're trying to predict the MEG response, so the MEG signal, starting as input as the spectrogram. So you build features using the spectrogram. These features are fed into a linear model that tries to output the MEG as a function of time. And this allows you to have basically for example, to say, okay, to which, if you have two audio streams and one person attends to only one of them, you can use these types of techniques to know, okay, to which speed signal, which audio stream leads to the best encoding model, and you can conclude if one person is mostly attending to one audio stream or the other. This is one application. So again, this is an example of encoding where before it was a decoding example. All right, all this that I showed before were completely supervised methods. So you had labels, and now I want to illustrate a couple of unsupervised methods. So this is an example of ICA, where here this is the raw EEG signal recorded on a few locations. So this is where your electrodes are. And by running ICA on this, I will not spend time to explain how this works, but the idea is to apply a so-called unmixing matrix to your EEG signals, and this will give you the so-called independent sources, basically sources which are as independent as possible in a certain sense. And I will just say that there are many ways of defining independence. This is typically one approach that is very much employed in EEG, but there are others. So this is a result that I assume was obtained with the so-called Infomax algorithm, where you can recover the latent sources, again, completely in an unsupervised way, only using independence assumption. You can recover and isolate the blinks, so the EOG, which you see relates to the topography of the eyes. Here you have an alpha burst, okay? Here you have here very strong theta waves, which are mostly here frontal. Here alpha, let's say occipital parietal alpha, and here some sources which are labeled as EMG. So here there are probably muscles just behind the ears on the neck. And here you have ECG, so this is the heartbeat also measured. So it's actually a very convincing picture showing you that from this signal where you mostly see one signal that looks completely the same for all sensors, it seems that all sensors see exactly the same thing. By unmixing them, you realize that there's much more stuff hidden behind all this. So this was the first unsupervised approach. In my lab, we worked for a few years on so-called convolutional sparse coding, which is a different way of unmixing EEG and MEG, using an assumption which is not independence per se, but the idea that the sources that you want to recover, there are a bunch of prototypical waveforms that are positioned in time, which means that you assume your model assumes that your sources, your latent sources, are just temporal patterns that happen only at a few time instants. And then when you apply this to MEG, illustrated here, you find these patterns that are actually mu waves that I also illustrated at the beginning. So you recover a so-called topography, and then here the spatial pattern, okay, so the topography, and here the temporal pattern of the mu wave, and again completely in an unsupervised way. All right, so why do these types of techniques work? I mean, if you step back a bit, what we are really leveraging in all the examples is the array of sensors. Okay, so we have many electrodes, and all of the electrodes are slightly positioned in different places. And in order to decode one condition on the other at a given time instant, like when we did time-by-time decoding, really what mattered is, okay, which feature captures the signal, and which feature in this specific case is which electrode, which sensor, and depending on where it is. So it was really purely based on spatial information. So why is spatial information so powerful? Although you could say that the spatial resolution of MEG or EEG is the limiting factor. So this is from a TICS paper from 2015, where I think it nicely explained. If you have here the folded cortex, okay, if you have a dipole which is here or here, so let's say that can be 2 or 3 millimeters away, by having your pyramidal neurons that are moving and kind of rotating by following the normal to the cortical sheet, you can have different orientation. So you're really at the same comparable location, but your orientation is changing. And remember that the field that you're measuring is very sensitive to the orientation. If I have my source and I rotate it, it was going to rotate completely the pattern that you measure. And so this is what is illustrated here just by rotating the source, even though it's very close spatially. So here, assume this is the folded visual cortex. If you move by 2 millimeters on the visual cortex, still you change the rotation of the equivalent current dipole, and you will produce a different topography. And this is this difference in topographies that will allow your decoder to succeed. And now, if you do it with here, this is an example. Imagining how cortical columns encoding for orientation in the visual cortex could produce different topographies. Okay, so different orientation of a bar on the screen, either horizontal or slightly tilted or vertical, will induce a topography that will change between the different orientations. Okay, this is also coherent with the first paper I showed you from the group in Alto. Okay, so new research suggests that MEG contains rich spatial information for decoding neural states. Even small differences in the angle of neighboring dipole generate subtle but statistically separable field patterns, and this implies that MEG and EEG is ideal for decoding neural states with high temporal resolution in the human brain. All right, so I mentioned this a bit before, and I'm going to do something which is very simple, but hopefully convincing. Imagine that you have two EEG signals that are collecting signals at channel 1 and channel 2. And channel time captures 2 times S of t. S is going to be a signal of interest. And N of t, see this as some noise, like a peripheral noise, like the noise of a car or a door opening next to the MEG. Okay, so these are the noise. And these are your second sensor. The second sensor now sees the signal from the source as S of t, so there's no 2. But since the signals, the 2 sensors are very close in space, they are pretty much corrupted, and here I'm going to assume that they are corrupted with very comparable noise, or even here the exact same noise. So if I just do what people call a spatial filter, or computing a derivation, just doing a linear combination of my EEG or MEG signals, okay, so x1 minus x2 gives you 2s minus s. Since the noise is the same, assumed to be the same, the noise will disappear, and you will get your signal of interest. So it seems, again, probably extremely naive, but the important part is that if you want to isolate the signal of interest and get a good SNR in EEG and MEG analysis, you should consider doing linear combination of your sensors. Looking at a single EEG electrode and conclude that you have an effect of interest either is, let's say, probably not so real, or the effect could be made much stronger should you consider an analysis that leverages your array of sensors by doing linear combination of your sensors. Okay, and again, if you want to do time frequency analysis, you can do time frequency analysis on individual sensors, but if you're really interested in some effects that are not so strong, it's really suboptimal to process one channel at a time. And the reason I showed you the power spectrum density just before, the power spectrum density can be easily dominated in amplitude by the noise. So if you just subtract or do linear combination, you have a chance to remove these strong amplitude artifacts in order to isolate your effect of interest. I hope the message was clear enough, and that you will consider multivariate methods for boosting the SNR of EEG and MEG. So then you have this nice paper from so Hubert is suggesting me that there's a break that is planned now. So I guess I should just maybe explain this slide and then I will do the break if you allow me to. Okay. So before the break, let me just basically advertise the work of Stefan Haufer in a few years ago at NeuroImage, also trying to explain why multivariate models can boost the signal-to-noise ratio when it comes to discriminating two conditions, which here are the blue and the red condition that imagines to be moving your right arm or moving your left arm. So he considers that you have two channels, X1 and X2, and each of these dots here is the measure of one time point over these two channels. Okay, so see that every dot has one observation of the data over X1 and X2 channels. So you have here the blue condition versus the red condition. And what is shown here is that if you only look at one channel, which is X1, then you can discriminate the blue and the red, but you see that the blue and the red histograms, they overlap. Okay, so they overlap, which means that your two point clouds, they are not perfectly discriminable by just looking at the X1 feature. And now if you look at the channel 2, you see that by projecting the data on the channel 2 axis, you're completely unable to discriminate the blue and the red condition. Whereas now if you allow yourself to look in an oblique direction, which is exactly this idea of projecting the data on a sub-axis, on a different axis, doing a linear combination of your sensors, you can much better discriminate your two conditions, the red condition versus the blue condition. Okay, so I hope this picture convinces you that by leveraging your pair of sensors, you can start to discriminate things and discriminate your experimental conditions with a much better effect size, much stronger effect size. All right. So induced and evoked MEG activity. So take-home message is don't do time-by-time decoding if your signal of interest is induced. So evoked activity is here illustrated by this small animation. This is raw MEG signals, okay? This was the continuous recording, okay? Continuous data with some low-pass filtering, so it's a bit smooth. Now, if I take 50 repetitions of the same experiment and I just average the 50 epochs or the 50 trials, Then you start to see some signal of interest appearing. You see that you have some deflections that are prototypical of a dipolar pattern. If you go towards 100, it's even cleaner. 400, you have a so-called clean evoked component, with here the signal close to zero during the baseline period, and here also some later components. Okay, so here you can guess that there's a number of evoked components which are all peaking at the different time latency. And from early as here 20, 25 milliseconds, the strongest one between 40 and 50 milliseconds, but also stuff happening a bit later. Okay, so this averaging only works because it's evoked, which means that the response of the brain is phase locked. The latency of the peak does not change with the trial. So now what happens if it's not the case? So here I'm going to illustrate time frequency analysis, where here I'm going to build a so-called spectrogram from this time course by sliding a window over the data. And for every slice of window, I'm going to compute the Fourier transform and look at the power of in the Fourier coefficients. All right, so let me move forward. Okay, so every window gives me a column of this image, and this column is just an image view on the spectrum. Okay, so what you see is that over time, the spectrum, okay, creates a bump, okay, so a blob, a strong peak here located at a given specific frequency, and you see that it's basically smeared over time, but also smeared in frequency. So behind this, you have a trade-off between temporal resolution and spectral resolution that I'm sure many of you know about. And this will depend on the size of the window you're using and the types of also, let's say, wavelet or things that you actually potentially do inside this window beyond a discrete Fourier transform. Okay. In the end, you get this, what people refer to as a time frequency plot, which is basically a spectrogram. Okay, so now if you have here 5 epochs, okay, 5 trials, and if you look basically at a given time instant, the oscillation, let's put it this way, this oscillation is always peaking at the same latency, which means that by averaging your signal, you get a very clean signal. If this is the case, then doing the decoding on the time by time will actually work. Okay. Now, if it's not the case, like illustrated here, you see that at the given time instance, sometimes you're in the trough of the oscillation, sometimes you're at the peak, sometimes you're in the downhill part, sometimes in the up part, which means that by averaging in the time domain all this, you'll get a very weak signal. So on the left, you have so-called an evoked / phase lock response, and on the right, you have an induced, which is not phase lock. So the way typically people do it is to compute a spectrogram of each of the trials and then averaging the spectrogram, basically killing the phase, killing the small temporal jitter in order to obtain a clean image. This is not decoding, this is just standard time frequency analysis in the MEG, EEG world. Now, you can also apply these types of thinking to the example of motor imagery, which is a very classical example of induced effects. Again, same fixture as before, 2 conditions, left hand and right hand movement imagination, different spatial pattern, and here a different deflection, so desynchronization, which is here on this specific pattern, a stronger decay for the right than on the left, and reversed on the other pattern. Okay, so let's do a bit of math before the hands-on. Okay, so in the end, again, you have 2 types of ML that you can do an MEG and EEG. Either you frame it as a decoding problem or you do it as an encoding. So if you do decoding, you're going to take whatever thing that describes the that is collected on your neural data, let's say the MEG and EEG, and you're going to predict behavior or the mental representation of whatever is present in the stimulus, versus an encoding model where you take features that you extract from the stimuli, okay? Let's say, for example, a deep net applied to a vision, or deep net applied to text, or anything that you can extract from the stimuli, and then you're going to use this to predict the neural activation, the neural signals. In the end, it's a matter of swapping X and Y. So X is your features, and Y is going to be your target. And what we want to learn is a function f that takes X as input and outputs Y. In the decoding, X is going to be the MEG data, and Y is going to be related to the stimulus. So in terms of notation, we'll denote the Xi's as vectors of dimension p, and the target, I will assume that is just a scalar, okay, just a single float, let's say a continuous float, or just let's say -1 and 1 in the context of classification. And you want to learn a function from Rp to R. So P, again, is your number of features, and you will have n observations, n samples. Okay. Just to make it clear what I mean by this, I'm going to consider binary classification problems, which mean that the target is just now discrete. It's either -1 and 1. And on purpose, I do -1 and 1 and not 0 and 1, and you'll see why in a minute. And my feature vector is here in Rp. So you can think as P as the number of channels if you do time-by-time decoding. It can be the number of voxels if you were to do this on fMRI. That can be the number of time points times the number of channels if you decode using a window of MEG and EEG. But that's basically going to be encapsulated in the P vector, in the P number here. Okay, so if you want to do a decoder on MEG, you may ask yourself, okay, what's the point? What am I trying to do here? So I'm going to consider that you have two conditions. People seeing either a picture of a face or a scrambled face. Okay, that can be a word or pseudo word, let's say binary task. What you want to know is when can you predict correctly these binary outputs? So with what, but taking data at which time instant, maybe taking data in which frequency, taking data in which subset of channels. These are the types of questions that you can ask. What you care often is, okay, can you make some kind of conclusion of where it's also happening in the brain? That's a bit more tricky. The when is much easier with EEG and MEG. And then what are the features? What makes the model actually work? So allow me to take this very toy example to make it very clear. I'm going to assume that I have two signals. Okay, two sensors, two EEG sensors. You're measuring stuff in microvolts. On purpose, I show you that what you measure is just not arbitrary number. It has a unit, and unit is basically what maybe makes EEG, MEG like quantitative neuroimaging or neuroscience techniques, because the absolute number of what you're collecting has some true meaning, maybe as opposed to fMRI, where you don't really look at the raw amplitude. You're always like maybe z-scoring or normalizing with some kind of baseline, and the absolute number that you're looking at the signal is not really important. But again, in MEG and EEG, you're measuring microvolts, you're measuring femtotesla, you're measuring femtotesla per centimeter, and you know what's the order of magnitude of the signal that what the brain can produce, and this can tell you if what you're looking at is signal and noise. Okay, I'll stop here, but keep in mind that these are quantitative measures. I have two conditions. I need to classify the reds versus blue. So red is scrambled face, and blue is a real face. What you can do is, okay, so now I've got features in dimension 2. Every xi is a dot, and the color is the target, and the target is either a 1 or a -1. What you can do is the following. You can average all of the red dots, okay? Average all of the blue dots, and this is what you would typically call the centroid of the red class and the centroid of the blue class. And you could say, okay, if I'm closer to the red centroid, it means that if my two sensor data is closer to red, I'm going to predict red, and otherwise I'm going to predict blue. So this decision function, okay, this decoder is nothing more than a linear decoder. And in the end, this like linear separation will allow you to evaluate your performance and count the number of times you've made a mistake. What I want to say here is that this linear decoder can be expressed in this mathematical form. The target, which means the color, is the sign being 1 or -1 of a linear function of the input features. Okay, so here I'm going to sum over features, so from 1 to p being the number of features. I do linear combination of my features plus some bias term, also called intercept. And in the end, your discrimination, your decision function is just a linear combination of the features. So B transpose xi, which is vector times vector, plus a scalar, and that gives you your prediction. This prediction you evaluated on left out data. Let's say you leave out 20% of your data and you count your errors, and this will tell you how good is your model. Okay, you count the errors on the left out test set. Okay, if you do logistic regression, basically you start by postulating that the log of the probability of being 1, let's say 1 is red and -1 is blue, the probability of being red given your MEG data is this numerator, and then the probability of being blue is the denominator. If the log of this probability ratio is a linear function, you're doing a logistic regression. What it means, after just postulating this quantity, okay, which doesn't come from nowhere, and if you know the theory of LDA, you end up with the same thing, but for logistic regression, you start from this, you postulate this, and just by postulating this and doing so-called maximum likelihood in order to optimize and infer the parameters beta and beta 0, which are basically the slope of the separating line or hyperplane, and here the offset, you end up minimizing a cost function with whatever gradient method you want. And in practice, you will add a tiny bit of regularization, let's say an L2 regularization or an L1 regularization. It doesn't really matter. What matters is that you have this linear form that gives you a loss, which is the log loss, and some kind of penalty. Also the important thing to have in mind is that you have a decision here that was made, which is the value of this hyperparameter that can have an impact on your performance. All right, now if I apply this on MEG and EEG, so this is an example, again, that you can look by clicking here. We have auditory left, like auditory inputs on the left here versus a visual flash on the left ME field. You do a time-by-time decoding, you have 50 epochs per class, and this is what you obtain using either here, using here linear SVM, and some, I would say, Monte Carlo cross-validation in order to obtain many cross-validation numbers. I won't spend too much time on this, but you can just read this tutorial to learn more about this. All right, when it comes to decoding induced activity, I think it's much less understood how to do it. If you think that you will do a time frequency plane and take the time frequency coefficients like the power in the spectrogram in order to classify, you're shooting yourself in the foot. You should not do this. There are two ways of getting a good discriminator, a good classifier for induced activity. I'm going to start with something that is pretty good and simple to explain. So I'm going to bandpass filter my data, for example, let's say between 15 and 25 hertz. Okay, you bandpass filter your data. So this is my bandpass filtered data, my sigma SI, okay, denoted C is the number of channels, T is the number of time points. And you compute the covariance, okay? You compute this matrix, which is channel by channel, that is the covariance of your bandpass filtered signals, okay? So this object here is just a matrix, which is C by C, okay? And it looks like a matrix like this. So here I'm showing you this on magnetometers in dimension 102. Okay. And now you could ask yourself, okay, now what if I want to classify using this covariance? Because the covariance will capture the covariation of the channels averaged over time. Okay. And if you think about this covariance is completely blind to the phase. Okay, if you have say any phase different, the covariance stays the same. If you take the time axis and you swap the columns and you shuffle the columns, you don't change the covariance. Okay, so the covariance will just capture the average covariation of your channels, no matter when the effect occurs. Okay, so now, how do you obtain features from the covariance? What you can do is do a so-called bilinear map. Okay, so you multiply your covariant on the left and on the right by a spatial filter. So Wj is just a vector of size c that you apply on the left transpose and on the right. So this is a row vector times a matrix times a column vector, and the output of this quantity is just a float. Okay, and ultimately what this captures is the variance of the signal, the variance of the data projected onto the spatial filter W. So you're kind of extracting from the covariance a single feature, by doing a left and right projection using this bilinear transformation. Then you take this quantity, which is a positive number because sigma is a PSD matrix, positive semi-definite matrix. This quantity is always positive. You take the log of this, and this gives you a real valued feature that can be negative or positive, and you use this as your new feature set. Okay, and then your discriminator is now expressed as follows. It's you take the sign of the sum from 1 to p of a coefficient beta j times this new feature, okay, log of this bilinear map. Okay. Now the million-dollar question is, how do you estimate W's? Because now your unknown coefficients, your unknown parameters are the W's, the spatial filters, and the betas, beta j and beta 0. And these are the seminal work on these types of things. And one idea is to use common spatial patterns. And I think in the interest of time, I won't go into the details, but I will just say the gist of this. They are very cheap to compute, and they are extremely like the bread and butter of BCI work for maybe 10 to 15 years. And they consist of estimating the covariance of every class, of the data on every class, and doing a generalized eigenvalue decomposition, where here sigma 1 is the covariance of class 1, and here you take the average covariance of your two different classes. Okay, this gives you spatial filters that you can apply, and then after learning the W's, you can do a linear logistic regression, and that's been done and is actually very efficient and very good to get a good SNR in your classification. But there's something also simpler, or at least I don't know if it's simpler, but at least hopefully also understandable, is to use so-called Riemannian geometry and Riemannian metrics. So the covariance, again, allows you to capture second-order statistics. And if you apply this on a bandpass filtered data, then you get the covariation of your signals in the frequency band of interest. If I give you a distance between two such objects, so two covariance objects, so here I take the so-called, what I call here the geometric distance, okay? So I'm not going to spend too much time on this, but let's say it's grounded on Riemannian geometry. Just remember that it's just a distance, a proper distance between two covariance objects. So you kind of whiten on the left and whiten on the right sigma 2. Then you take the matrix log of this, which means it is the log that you apply to the eigenvalues of this matrix here. So the lambda k are the eigenvalues of this operator here. you take the sum of the squared log of the eigenvectors, and so eigenvalues of this object, and this gives you a distance. Okay, not going to spend more time on this, but it's just a way to get a float, which will be 0 if the two matrices are the same, and otherwise it will deviate from 0 positively. And then once you have this, you can do the neurocentroid algorithm I illustrated just before. So if you're able to compute the mean covariance of the class 1 and the class 2 using this formula, okay, you can even do the empirical covariance. That would be already pretty decent. And then your prediction rule, okay, which again is frequency resolved because you estimated this covariance in a specific frequency band. You can say, okay, if the distance between my covariance of epoch I is less for sigma 1 than for sigma minus 1, then I'm going to predict 1, and otherwise I'm going to predict minus 1. And this is what Alex Barachon and co-authors called historically the minimum distance to the mean. So it's the mean using this Riemannian metric. And that led to the first seminal work of leveraging Riemannian methods to obtain progressively state-of-the-art performance when it comes to decoding on EEG and MEG data. And you can look at the PyRiemann software to do these types of operations. All right, I'm going to arrive towards the end of the slides, and we'll have at least 45 minutes to do to play with data. I want just to say a few things, which is when you do your cross-validation, you should generalize on and test on unseen data. It's obvious to everyone, probably, but remember that a proper validation requires to split your data in 3 between the training, the validation that allows you to tweak your hyperparameters, early stop your training loop in your deep learning models, and then evaluating on your test set afterwards. All right, so we'll use the MNE software in a minute. Okay, so we'll use what's also called MNE-python, which is a Python implementation of the historical MNE software that is now, let's say, feature complete, and that allows you to do the processing of different modalities beyond MEG and EEG, like SEEG, ECOG, or FNIRS. And I would like to conclude with 2 empirical results. The first one from a paper of mine more than 10 years ago, showing you on the decoding, actually was with fMRI, of the decodability of 2 conditions, which are either face and houses, depending on the number of training sessions that you've used. What you see is that your classifier reaches almost a perfect accuracy if you take the 10 sessions of data for training, and here evaluating always on the 10 left out session, and you see that performance ramps up very, very high. What it means is that I would encourage you to look at this so-called learning curve, which is how well your model improves when the training data augments. And if you see a curve that increases, for me, that suggests that you can believe in what you are reporting in terms of score. If this line is very noisy, then I would be skeptical. And then also this work on a paper from Gaël Varocco, which I think is for me inspiring, and I let you meditate this, which is something that is completely counterintuitive compared to what I showed you here. Here I showed you here that you have more data, you learn better. And what Gaël shows in this paper, by doing some meta-analysis, is that if you increase the sample size, if you have more subjects, here it's in the context of diagnosis of different conditions, psychotic conditions, Alzheimer or depression, or autism, you get things that are insane. You see that the cross-validation is actually decreasing with the sample size, which is against any intuition that you may have in machine learning. You would say, okay, the more data, the better. I need big data to learn big models. But here, the more data you have, the worse is your classification performance. And I will let you meditate on this and maybe suggest to me in the chat why this is the case, and I will react afterwards. Okay, so we'll now switch to the material and spend a little less than an hour to play with data. So most of the work that I've been shown today was done where I was a researcher at INRIA with different funding sources, and I'm not at INRIA anymore. I work, like Hubert, we work at Meta since recently, and that's it. All right, I guess now you should be able to see something like this, which is the materials that you can either clone and download locally. You can also open this repository using Google Colab, and you should see something that looks like this. So when you are good, can you just put me a thumbs up here so I have an idea if you are, and don't forget to put me in the chat your explanation of why Gael observed what he saw in his meta-analysis.
If anyone has any problem running the notebooks, let me know.
Are we good?
You guys good? Yeah? Yeah, Alex, I think we can continue.
Okay. So I think it's important to start with the first notebook. I want to show you a few things which are generic things about MNE. And then we'll do the temporal decoding. And if you already know MNE quite well, you can maybe jump to more advanced notebooks. But I guess I could spend 4 hours on these notebooks, so I'll just cherry pick a few things. Okay. All right, is it big enough? Probably like this.
Yep. Yeah, it should be.
Okay. All right, so import a few packages, so NumPy, Matplotlib, and then import MNE. Change the log level to avoid having too many things printed to my screen. And just an important message that if you need any help with an MNE function, just use the question mark at the end of the function or class that you want to learn from, and you should see the doc. Okay. So we'll use the MNE sample data. So if on your local machine, if you don't have the sample data, it's going to download it. If you're on Colab, it's going to download it too. So I assume that if you have not done it, it will probably take 4 or 5 minutes to download. And just while it's downloading, you can just listen to me and I'll show you the raw data while it's downloading in the background. Okay? All right. So I'm going to read the data using a read row function. So you have a bunch of read row functions. Here the data is stored in FIF, so I'm going to use read row FIF. But you could use other types of data, like read row CTF if you have CTF MEG, or you can use EDF, or for EEG files, you can use EEG lab files that you can support various file formats. So here I'm going to read my data using read row FIF. And you see that my data contains 376 channels for this number of time points, which corresponds to 277 seconds of data. And the data in memory is roughly 120 megabytes. So MNE objects have attached an attribute which is called the measurement info, and the attribute is just called info. So if you look at the raw.info attribute, it contains a number of things. Here, it will show you information about what are the channels that are considered to be bad. It will tell me how many gradiometers I have, how many magnetometers, how many steam channels, how many EEG, how many EOG. Okay? And the other information that are important is the high pass. So it means that the data during acquisition have been high passed at 0.1 hertz. And here the data that I make you manipulate have already low pass filter a posteriori at 40 hertz. I give you I make you manipulate this data with the low pass at 40 because they are much smaller, because I've been downsampled, and it makes your analysis much faster. And you can see that the raw.info is nothing more than a Python dictionary, which means that you can access the attributes using the square bracket and getting the key. For example, one key, which is the sfrec, or sfreq, frequency. So the data here have been resampled and downsampled at 150 hertz. I've got two bad channels, okay? So MEG 2043, one EEG. Raw.channel names give you all the channel names of the present in the data. And raw.channel is nothing more than a list. So you can index this list and slice it to obtain, for example, the first 10 channels. Pierre, how are we going in the room? Any too fast, or how are things going? Okay. No feedback. Means all good?
We can't run it yet because it's still downloading the data set. It's stuck at that cell phone.
Okay, so, all right. So let me then do something, which is, let's just plot the data. So let me illustrate just two things that both of you who don't work in Colab will not be able to do. So if I do a row dot plot, if you are on your laptop, you should see the same window as me. If you work on Colab, you will see a static image. But here, let me show you the raw signals using the data browser that is now present in MNE. Okay, so here you can just browse the different the data. Okay, and if you press here or H, you will see a number of shortcuts that you can do with the data browser. If you press on on B, okay, B stands for butterfly, okay, you will obtain a so-called butterfly plot where now you have one line, okay, per type of channel. And you see that the data contains in light blue the gradiometers, in dark blue the magnetometers, and then in black the EEG channels. At the bottom you have the EOG, and here you have the so-called steam channel, okay, which will contain information about the paradigm. So you see that if you have a blink here, this appears everywhere, okay? And what you can maybe guess is that here you have these peaks. Let me undo the butterfly, okay? So here you see very nicely here, okay? This peak that you see here is actually heartbeats, okay? So these are the physiological artifacts that I illustrated before. This is the blink, and these are heartbeats that you see in the here on the gradiometers, but they're also present in the magnetometers and even more strongly in the magnetometer. How are things with the download? Is it still downloading?
You good? Yeah.
For me, yeah.
You still don't know?
Yeah.
Okay.
Is there a way to get it on GitHub so you can download it? I think it's the internet might be the problem.
Yeah, internet is a bit slow here, and if everyone is downloading at the same time, it might take a few minutes anyway.
All right, so let's spend a few more minutes then on the raw data. Okay, so here, these are the gradiometers. Then we have the gradiometers. And here, if you look here, this channel is grayed out, okay? And this channel is grayed out because it's typically a bad channel, a channel that was corrupted during the acquisition. And just by clicking on the label here, you can untoggle, you can remove this channel and mark it as bad, okay? And there is another channel that is bad, which is an EEG channel, which you see here at the bottom. And this EEG channel is bad because it basically the electrode has lost contact. So the EEG electrode is pretty flat. Okay, so these are the two examples of a channel that is globally corrupted, globally bad. So basically what's happening is that we're just going to remove these two channels from the analysis. These artifacts are permanent, but there are other types of artifacts which are so-called transient. And so if I go back to butterfly mode, and I kind of make you look here, so you see that there's one gradiometer that has this kind of basically deviation. It deviates from the with a small fraction of time, and this is what you see here. Okay, so here you see that the gradiometer has this square wave, and this is what is called a flux jump in MEG, and this is typically a classical transient artifact that you have with squid sensors. Okay. So in order to illustrate and maybe gain a bit more time, I'm going to press A, which is the annotation. So I'm going to add an annotation, and I'm going to do add, and I'm going to call this a jump. Okay. So I'm going to create some annotations which are jumps, and so here I'm going to annotate this as a flux jump. Okay. We can see if we have other flux jumps. Let's see if we have more. Probably here we have another flux jump. Here. 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 How is the download going? So here you see that you have a huge artifact in the EEG. Okay. Let's see which channel it was. Okay. Okay, it seems it's it for the flux jump. You can do same thing, bad for EOG. Okay, so let's go back. Okay, so when do I have big blinks? Okay, so here you have a blink. Okay, this is probably too wide. Up like this. Okay, I want EOG. Okay, so I guess I give you the idea. Okay, this is how you would basically manually curate your data in order to identify all the windows of data where you have a problem. Okay, it's still downloading.
For me, it worked on Colab. When I opened it on Colab, it kind of downloaded in a minute.
Yeah, on Colab it will be fast. Yeah. All right, so that gives you an idea of the types of pre-processing you may want to do if you do your data curation completely manually. Does it make sense to proceed, or are you still stuck if you're in the room? And the people remote, are you good?
So we had some people trying to run the visualizer in a separate window. So installing PyQt5 seems to fix the problem.
So if you install MNE using pip install MNE, then you have a you're not taking the easiest route. If you just do conda install MNE, it should install everything, including PyQt5 and everything you need. So, yeah. So this is one approach that will work on Colab, okay? And if you want the Qt browser, then the easiest way is to conda install, something you cannot do on Colab. Any other question in the chat?
We have Rosa who asks whether there's a list of artifacts or artifact examples signals somewhere. I'm trying to find, I think there's a tutorial in MNE.
There's a tutorial on artifacts in MNE that tries to show you some small windows of, okay, what is an artifact? I would say the short answer is, if you see all your channels with a big deflection at the same time, it's a big amplitude artifact that is spread across all sensors, and that's most likely an artifact. If you see one channel that is very different from all these others, including the one in the neighborhood, then it's most likely an artifact. If you have different channels that look the same and they are not producing a big deflection all in the same direction, then it's probably a true signal. Is there any other question?
I don't see any other question in the chat.
Jan, in the room, is there any?
Yeah, so I'm moving a little bit around the room. I think everyone has downloaded the data now. Is that
Okay.
right? So yeah, I think we can continue, and I'm
Okay.
watching and making sure everyone is.
Okay. Good. All right. So I assume that you now managed to reach this point. So next thing I illustrate here is how to know what is the type of a specific channel. Okay. So here mne.io.pick the channel type will give you the type for the channel of index 75. So you see that it's a gradiometer, and the channel of index 320 is actually EEG. Okay, so here the CHS key contains a list of the channel, let's say if you want to see the channel metadata, which are the channel locations typically, the channel types, the units, and a number of relevant information for each of the channels. And this structure is a list of dict. Okay, so for example, the first channel, okay, is of kind MEG. These are the amplitude scaling. What matters is the types of coil. You see that it's a vector view planar gradiometer. This is its location, which contains location and translation. This is the unit. You see that the unit is in Tesla per meter because it's a gradiometer. And this is its name, and it's defined. This location is defined in the device coordinate. Okay. These are the kind of the internals of the MNE info data structure. And we can do the same for another channel. So in this case, this is EEG. This is the location of the EEG, and now this time the channel is expressed in a different coordinate system, which is the head coordinate system. And you see that the data is now stored in volts. Okay. So since we have all this metadata of the channels, we can just do things like this, like a plot sensors, and they will plot a 2D map where it shows you here the location of the gradiometers, and you see that we have one red dot. This is one gradiometer which has a problem. Okay, so accessing the data can be done using a NumPy type of approach. So if you just access using row.square bracket of your row object, this will index the channel direction, and this will index the time direction. And here, by slicing your row instance, you get the data and the times. Okay, so you see that by this slicing, you get a NumPy array. So if you look at the type, the type of data, it's a NumPy array. And if you do data.shape, okay, it's 376 channels, and you have 10 time samples. And it's the same thing for the time. Time now is just a 1D array that contains the time samples here expressed in seconds. Okay, so what it means is that you can easily here. So here I'm plotting only the EEG. Okay, we've done this before. And yeah, I guess that's pretty much it on visualization. Okay. So you can filter the data. So here, this is your raw object. You read it. Okay, so now I'm rereading. So I mean, I'm going to lose all my annotation. It doesn't really matter. I'm going to read my data again. I'm going to filter it between 13 hertz and 30 hertz. That gives me a new instance that has now a low pass at 30 and a high pass at 13. Okay, so you do row beta dot plot, and now this is a plot only in the beta band. All right, so the small exercise, let's do it together in 1 minute. So plot the 10 first seconds of the stimulation channel STI-014 using matplotlib. Okay, so if I just follow the instructions, if I do row.ch name.index of STI-014, it tells me that it's 312. So let's say I'm going to call it this index. Now if I do data and then times equal to row and index and then times, okay, you're going to get your data. Oops, what did I do? Not times. Sorry, the 10 first, the 10 first seconds. So here, my sampling rate, so row dot info sfrec is 150. So if I multiply this by 10 to have 10 seconds, and I take this as an int, okay, this is the number of samples that corresponds to 10 seconds. Okay, so I'm going to just do this. And this is going to give me data, which are an array. I've got one channel, one sensor for this duration. Okay, so now I can do plt.plot. Careful, plt.plot will plot the columns of your array. You see that the array is 2D, so you need to transpose it. And here the time axis is in the time vector, and this will plot the steam channel. So here I'm plotting the steam channel, okay, for 10 seconds, and you see that the steam channel is mostly zeros. First it jumps from 0 to 2, then it jumps from 0 to 3, then 0 to 1, etc. Okay, any question on this?
No.
No?
No, we're good.
Okay. Okay, so basically what this steam channel contains, okay, so let me this steam channel that you see here, it contains information about the paradigm, okay? And this will allow us to define the events. So if I just do MNE.find events, looking at the events on the STI014 channels, this contains the events, okay? And the events is nothing more than a NumPy array, where here I've got 319 events. And if you look at the type of events, is just a 2D array. But if you look at the first 4 rows of your events, you will see that here the fact that you have a 2 here is nothing more the fact that here you have your steam channel that goes from 0 to 2 first, and then from 0 to 3, and then 0 to 1. Okay, these events will tell you when. Okay, these are the sample number. Okay, which time sample does the steam channel goes from 0 to 2. So it goes from 0 to 2 at this channel, at this sample number. At this sample number, it goes from 0 to 3, etc. Okay. So, for example, if you want to know, okay, how many events have an event of type 4, you see that by just using the simple NumPy syntax, you have 70 epochs of type 4. Okay. So let me visualize the events. If I do mne.viz of plot events, this is pretty much everything that happened on the steam channel. Okay, so you have different conditions. Okay, you have condition 1, 2, 3, 4, and then 5 and 32. So in order to understand what these conditions mean, you need to know about the protocol. And the protocol, you need to know about the experiment. So MNE allows you to encode information about these events using an event ID, which is a dictionary, where the key is going to be the stimulus name, okay, for example, the visual left, and the value is this integer, which is 1, 2, 3, 4, 5, 32. So here I define my event ID, and then I can do viz of plot events passing the event ID, and you see I only put 1, 2, 3, 4. So it's giving me a warning saying that there's some that are missing, but this is on purpose. Now I only have 1, 2, 3, 4, and now I know that 1 is a visual stimulus on the right ME field. The green is visual left, orange is auditory right, and blue is auditory left. Okay, and you have the number of times each of these stimulus was actually presented to the subject. So you can actually plot the data with the events. So this is this line that you see here that kind of allow you to see when these stimuli actually are present in the data. Okay. All right, so now we need to create a so-called epochs. So the epochs are these chunks of data that you're going to extract from the continuous raw recording. So I'm going to take chunks of data which start 0.2 seconds, so 200 milliseconds before the stimulus, and 500 milliseconds post-stimulus. Okay, these are the T-min relative to the stimulus onset, so the event, okay? And then with a specific baseline that will be from the beginning, which will be minus 200 milliseconds to 0, and this is going to define my baseline period. Then I define here the rejection dictionary, which will allow me to reject epochs that have a too strong peak-to-peak amplitude delta. So I told you that the artifacts are mostly amplitude artifacts in EEG and MEG. So the crudest way of doing this, and I mean, there are different ways of doing this, but this is kind of the 101 approach in MNE. You define a dictionary and you say, if during my epoch of here 700 milliseconds, there is at least one gradiometer that has a peak-to-peak delta that exceeds this value, then the epoch is bad. And this applies, for example, in the case of EEG, if there's an EOG channel where the deflection from min to max during the epoch is more than 150 volts, 150 10 to the minus 6 volts, which is 150 microvolts, then you reject the epoch. Okay. So here now I'm going to pick only the MEG channel. So I'm going to restrict my data to the MEG and then construct my epochs. So my epoch is formed from the raw object, the events, to know where to crop the epochs, what are the types of the epochs, what is the Tmin and the Tmax, the peaks, so what channels do I want to consider, how to baseline, and how to reject based on peak-to-peak amplitudes. So once I have this, I get an epoch structure that contains all of my conditions extracted from the data. So here you see that the data have not been loaded, and it turns out that all the events that still are now good and bad. Basically, reject was actually not taken into account. So now if you drop the bads, after dropping the bads, you go from 73, 70, or 72 to now 55 auditory left and 61 auditory right. And so you've reduced your data. Let's say I've removed maybe 15% of my epochs because of some problem on either a gradiometer or magnetometer or some EOG. So you can plot the drop log that you see here. Okay, so it shows you that most of the epochs, so you see I rejected 17% of my data, mostly due to a blink because I rejected because of this EOG, but there's also an MEG channel which also is causing some rejections. So I mentioned during the slides that you can look at the power spectrum density. So if you do raw.plot.psd, they will show you the PSD. I guess it's appeared in the background. So I'm going to close all. And here, where is this? Interesting. Okay. All right, so this is my power spectrum density. You see every line is one channel, okay? And for example, if you select this frequency interval, you see as a heat map or the topography where the power of the respective channels. Okay, so you see that here by looking at the frequency around maybe 7 or 8 hertz, you capture these types of bilateral hotspots. And it turns out that I'm pretty sure that this is the auditory evoke response that is just bilateral. And that is a slow wave that is on this order of the frequencies, on this typical pre-frequencies. You can also look at maybe this is possibly an artifact, and you can see, and actually it's pretty clear, looks very noisy, and this is an artifact present in the magnetometers. Okay, so you can also plot the epochs, which is what you see here. Now you have all the epochs, now you have all the epochs that are present. If you, for some reason, you see that one epoch is back, for example, this one you still contains the flux jump, you can click on this and decide to remove this epoch from the analysis. And you can browse your epoch to see if there's still some issues with certain channels. Okay. All right, it's getting to extracting evoked responses. So here I've got all my epochs. I can average all my epochs. That will give me a so-called evoked object that you can print, but you can also plot it. And this is what I'm going to do here. This is my evoked object, but this is interestingly, you need to realize that here I averaged the visual data, the visual left and right, and also the auditory. So I kind of averaged apples and bananas. What I want to highlight is that now if I select, so if you do this, I think it's an important thing to understand about MNE. If you do epochs and you square bracket and you access epoch like as if it was a dictionary and you say auditory left, you're going to get only the epochs that correspond to auditory left. And this is only 55 epochs. I could do the same thing for auditory right, and then I will get 61, and which something that is for me really neat. If you just do epochs and you do auditory, it will take both auditory left and auditory right. And the reason is that the slash in the name here means that the trials are basically the auditory, sorry, let's say the word auditory and the word left, just see this as tags on epochs on your conditions. So if you want to do epochs left, then you will get the auditory left and the visual left. So this allows you to basically select your epochs based on categories, okay, that are expressed in the name of your conditions. And so now if I only select the auditory left and I average them and I plot this, okay, you get this nice evoked response. And you can actually select. So here, if I select this time window, you see a very clear dipolar pattern on the magnetometers and the gradiometers. And if you look now a bit later in time, okay, you will see it lateralize on the opposite side. So here now you have the left, the auditory of the left auditory, the response of the left auditory cortex that you see here on the left. Okay, so you have these two bilateral response to the left auditory stimulus. First, the first peak comes on the contralateral auditory cortex on the right for left stimulation, followed by an ipsilateral activity here a few, let's say, I think something like 17 milliseconds later. And this is your left auditory dipole, left auditory response. Is there any question on this?
Are you okay? Sure. Yeah, I think we're fine.
Okay.
People are nodding that they're okay.
People are what?
Nodding.
Okay.
They seem to be doing well.
Okay, good. So I think I won't have time to do too much, but I'm going to just do the next notebook, which is the illustration of what I showed you in the slide, which is the temporal decoding. So we're going to apply this time by time decoding. So let me just clear my output. Okay. So hopefully now things should be fast for you because your data have already been downloaded. Just import MNE. I take my raw data. Okay. I apply a high pass filter. Okay. We can discuss if it's a good idea, but let's say I'm gonna just do high pass filter to remove the drifts. And in the end, I have data with a band pass filtering between 1 and 40 hertz. Okay, so I'm going to define my epochs exactly the way I've done it. I find my events, that gives me my events. Okay. From these events, I can define my event ID. Okay, so here I say auditory left is 1, auditory right is 2. Here I plot my two conditions that I would like to discriminate. So auditory left stimulus or left or right auditory stimulus. I'm going to define my epochs. So here I'm going to go from 100 millisecond pre-stim to 400 milliseconds post-stim. I don't apply any baseline because I have a high-pass filter in my data, so I've kind of DC corrected my signals. Here I'm going to do the decoding using EEG and MEG, constructing my epochs. Okay, so all the epochs now are good because the rejection has been done during the loading. And so we're getting there. First, I'm going to look at the evoked components for the evoked left, which is what you see here. Then I've got evoked right, and here is the contrast. So here, this is just a plot of subtracting the data from left stimulus with the stimulus on the right. Okay. So ultimately, if you're able to decode linearly your data, it means that by subtracting the data, there should be something. And this is what you see here. All right, so let's plot a few topographies. So this is a topomap plot of the EEG, okay, as a function of time for the left, for the right, and for the contrast. Okay, so it seems fairly blurred and noisy. Okay, so that's EEG. And now we're going to do the decoding. So to make sure that the accuracy of the decoder is at 50%, we'll simplify the interpretation of the plots. I'm going to equalize the event counts to have exactly the same number of epochs on each condition. So after doing this equalized event count, I got 54 auditory left, and 54 auditory right. Okay, so I'm going to have 108 samples and as many features as the number of channels. So from this, I need to construct what is X and what is Y. Okay, so the Y constructed as this, okay, is going to be an array of dimension 108, okay, because I've got 54 and 54 on each of the classes. And if you look at what's the value of Y, okay, this is a bunch of here 0 and 1s. I mean, scikit-learn can deal with 0 and 1, otherwise I could put -1 and 1, doesn't really matter, at least for scikit-learn. And here you have your sequence of conditions, condition 1 and condition 2, so auditory left or auditory right. Now you can get the data. So here I'm going to get the data using taking only the gradiometers. So I'm taking the good gradiometers. I've got 203 gradiometers. So this is going to be my features. So this is my samples. These are my features. And here, this is the time, which means the number of different classification tasks that I would like to do. So I'm going to typically run, later on, a classification for each of the 76 time instance. Before doing this time-by-time decoding, what I do here is that I change the shape of X by saying, okay, now I'm going to take all time point and all channels and just see if I can decode anything at any point in time. And what you see, so you flatten your feature space. Now this value is all channels, all time points. I'm going to do a logistic regression, doing a stratified k-fold using 5 split. I make a pipeline, which is a standard scaler and a logistic regression. And then I do a cross-val score. Okay, using a ROC AUC, let's just ignore this detail for now. Computing all my scores, and in the end, you see that I can discriminate my left auditory data and right auditory data with a cross-val score in ROC AUC, which is on average 0.88, which is pretty good because chance level is at 0.5, and with a standard deviation, which is not too big, which is 0.01. So you have a clear, significant effect of decodability between auditory left and auditory right. So this does not tell you at all when in time is the discriminative performance present. So to do this, I'm going to do the same types of decoding, but now at every time point. So in MNE, you don't have a cross-val core function, but you have something that we call cross-val multi-score that will basically broadcast the decoding to the time direction, So my model, okay, my pipeline is going to be a scaler, okay, which is now a transformer implemented in MNE, a vectorizer, and log-reg as classified. Okay, X is just the data, which is now 3D, so epochs, channel, and time. This is my target, and I do the cross-val multi-score, and then you get a ROC AUC, okay, which here, if you look at the scores, okay, scores.shape, okay, oh, what did I do? All right, so we're not yet at the time by time. Sorry, I was too fast. So this is not doing time by time yet. This is redoing the same thing as we just did using all time point. This is why you have the vectorizer that you have here. So now you re-obtain the same thing as we just did before, except that we do a scaler which is scaled by channel type, and here using gradiometers. It's just the scaler that has changed. I didn't do a standard scaler, it's just a scaler which is informed by the channel type. And as you see, it's a slightly better scaling. All right, so now one exercise that I was asking, I'm speeding up because I think we're out of time. Here I'm answering the question, is it better to collect EEG MEG gradiometers or MEG magnetometers, and in the sense that what modality, what types of channels gives you the best effect size, the stronger effect size, and your best decodability. And this experiment is pretty simple to do. I'm going to redo the same analysis, but now I'm going to select gradiometers, magnetometers, and EEG, do the decoding for each of the three modalities, and see what I get. So let me run this, and you see that with the gradiometers, I've got 92% classification score. With the gradiometers, I've got 88, but with EEG, I only have 74. So the take-home message is that EEG is cheap and very easy to collect, but of course, I'm a very strong MEG advocate for the people who know me, but you have a much clearer effect and a much better SNR and a much stronger discriminability with MEG than with EEG. You can do this decoding now over time, and I will just run this cell so you can see what's going on. So here I'm doing the decoding at every time instant, and you see that the strongest effect is here and here, and they correspond to when one auditory cortex starts to ramp up and the other one has not done yet. And the other peak that you have is when one is back to baseline and one is still present. So this is why you have these two peaks. And I guess I will just stop here. I encourage you to do the exercises. And if you are deep learning fans, you can do the last notebook, which was prepared by Hubert, and which does basically deep learning on sleep EEG, showing you how to train the ConvNet to classify sleep stages. And with this, I think I should stop now and potentially answer any question you may have.
Thanks so much, Alex. There's a few questions in the chat. So the first one is pretty technical. Like for machine learning models, when participants don't have the same numbers of clean electrodes, do you have a favorite way to reduce dimensionality and find a common set of channels for all participants, assuming a high density EEG? For example, drop the electrodes that are not clean for all subjects, do a PCA clustering of electrodes, regroup them based on central, frontal, parietal, temporal, etc. What are your thoughts on that, Alexandre?
I would say your baseline is taking the intersection of all the channels which are good across all your subjects. And you may find it naive, but last year I co-organized a challenge at NeurIPS where the game was to generalize a classifier to the different set of different experimental data sets. So train on one data set and generalize to another one, and the electrode number were different. And all the winning teams made it work by just subselecting the electrodes to have the same electrodes on the two data sets. So doing this intersection is probably already a very strong baseline. What you can otherwise do is interpolate all the bad electrodes for all subjects, and now you have the superset of all the possible electrodes. So you kind of, if imagine you have 100 subjects and 100 electrodes, and every subject has a different electrode which is bad, the intersection doesn't work. You have nothing left. Okay, so what makes sense is to do the interpolation, which is the option 2, which I just mentioned. And otherwise, you have more clever techniques. I can send you some references, like, for example, Riemannian methods. There are techniques that I can deal with cases where the electrodes are actually changing for each of the subjects, and you want to generalize your decoder with you train on 20 electrodes and you want to generalize to 18 electrodes, and you don't want to throw away your 2 extra electrodes, or your classifier is pre-trained. And for example, with Riemannian methods, there's a paper from Pedro Rodriguez, who is now a researcher at INRIA, that he did during his PhD that can deal with this.
Fantastic. Thanks a lot. I think there's another question. I think the last one, at least on the chat, which will be a great way to end the session. Do you think that 1,000 channels EEG can replace fMRI, or maybe am I out of a job? That's my question.
downloading them?
I don't think so. I think you still have a lot of of good years by doing fMRI. No, what is more for me? What could be a game changer with MEG is the new MEG sensors that allow you to have high density MEG at the skin surface, so-called OPMs, optically pumped magnetometers, which are kind of soft EEG cap with MEG sensors that potentially could allow you to have sensors that are closer to the brain. What makes MEG, one limitation of MEG is the fact that between the source and the sensors, the attenuation of the signal decays quadratically with the distance. Okay, so if you go 2 times further away, then the signal will be divided by 4. Okay, so if by moving the MEG sensor, by being able to sense the MEG field twice closer to the cortex, you can have a huge boost in SNR. So imagine that you can have 100 of MEG OPMs on the skin and not 2.5 centimeters away. That can be big.
So actually, you're answering another question which I had asked, which is whether the anatomy of the subject impacts your measurement. So let's say you have a measurement of however many microvolts. This may actually reflect how thick the meninges, the fat, the skull is, right? Like, because that's going to change the distance to the source and alter the absolute value of the measure.
So how is the anatomy affecting your data? So if you follow the beginning with the orientation of the pyramidal cells, you realize that the folding is critical to get the signal of interest. If your signal was a flat surface, you would be in big trouble to do anything. Okay, so the fact that the cortex is a huge mess of folding is a blessing for your ability to see things from MEG. What it also means is that you can have cancellation effects. So imagine that you have sources that are pointing towards each other. They are just linearly going to cancel each other. Okay, so this, you can tell me this is unlikely to happen, but the truth is that, well, you never know. It is not like in fMRI where a voxel is a voxel, right? So there's no chance that for one subject, basically, just the ball signal is not there. But what's happening is that you have some subjects for which the signal of interest is much weaker than all the other subjects, and this is probably due to the anatomy, which is different, or some canceling effects that are present.
Okay, so that actually answers why even with 1,000 sensors you won't get fMRI, because this type of cancelling is unavoidable.
And it's also, this is part of the answer. The other answer is that the skull, typically in EEG, is very insulating. So see the skull as a lens that will blur the signal of interest. It will smooth. So even if your neuronal pattern is very spatially resolved, when you propagate it through the skull, it will look blurred.
All right, so it acts like a low-pass filter,
low spatial, exactly. It's a low spatial filter, like a low-pass spatial filter.
So the effective resolution of the technique has a ceiling, no matter how many
exactly.
samples.
Exactly.
Excellent. Well, we're going to end the session now because there's food downstairs for this person.